The mathematical fingerprint. How we lock a vector field into place. Imagine you are trying to describe the flow of water in a tank or the invisible paths of electricity in a wire. You might think you need to measure every single point to know the whole picture, but nature has a secret fingerprint system. This system is known as the Uniqueness Theorem, which proves that if you know just 3 specific things about a field, there is only one possible way it can exist. The 3 anchors of a field. To define a field uniquely, you must anchor it in 3 ways. The source control, divergence. This tells you where the field is being created or destroyed, like a faucet or a drain. Without this, you wouldn't know the push and pull of the flow. The twist control, curl. This tells you how much the field swirls around a point, like a whirlpool in a stream. This accounts for the rotational behavior of the field. The frame, boundary conditions. Even with the push and the swirl, a field could still have an arbitrary background flow passing through it. Fixing what happens at the edges, the walls of your container, acts as a frame that prevents any extra flow from leaking in or out. The narrative of the solution. To prove that these 3 anchors are enough, we use a clever logic. Imagine 2 different fields, let's call them field A and field B, that both claim to have the exact same sources, the same swirls, and the same flow at the boundaries. If we look at the difference between these 2 fields, we find something remarkable. This difference field has no sources of its own, no swirl at all, and no flow moving through the boundary. Mathematically, we can describe this difference as a scalar potential that follows a specific equilibrium rule called the Laplace equation. When we look at the total energy of this difference field across the whole volume, we find that because it is pinned down at the edges and has no internal movement, its total energy must be 0. If the energy is 0, the difference itself must be 0 everywhere. Therefore, field A and field B must actually be the exact same field. Demonstrating the theorem. To visualize this locking process, we can look at 3 distinct stages of definition. Demo 1. Building the field. This demonstration shows how a field is constructed from its components. First, we see the divergence phase, where the field flows straight out from sources like a starburst. Next is the curl phase, where it swirls in circles like a wheel. Finally, when these are combined, they create a specific, unique spiral pattern. Demo 2. The 2 ways to lock the boundary. This demo shows that there are 2 ways to frame the field at the edges. The first way is fixing the normal component, which controls the leakage or flux through the walls. The second way is fixing the tangential component, which controls the slide or circulation along the walls. Demo 3. The side-by-side comparison. This final demonstration places the 2 boundary types next to each other. Even though the arrows at the boundaries look different, one set pointing through the wall and one set pointing along it, the internal field is identical in both cases. This proves that either boundary constraint is sufficient to mathematically freeze the field into its unique state. Why it matters. This isn't just a math trick. It is the foundation of modern physics. In electromagnetism, for example, once a physicist calculates the distribution of charges, sources, and currents, swirls, and knows the boundary conditions of a device, they can be certain that the resulting electric field they find is the only one that can possibly exist in nature for that setup.